Chapter 8.5, Transformational Geometry, Symmetry, and Tessellations. So in this chapter, we're going to be taking all of our polygons and other shapes that we have investigated and learning how to sort of manipulate them, move them around, and make sort of fun patterns with them. So first, we have to talk about rigid motion. The act of moving a geometric figure from some starting position to some ending position without altering its shape or size is called a rigid motion or transformation. We will talk about three types of rigid motion: reflection, translation, and rotation. So note that because we are just taking the shape and moving it in some way, whether we're sliding it or rotating it or flipping it over, any of that isn't really changing the shape. So we have this word congruent that we've talked about before. Any transformed shape using a rigid motion is congruent to its original shape. It's just taking that first shape and moving it over. It's the same shape, same size, and all of that in the end. So our first type of rigid motion is a reflection. A reflection is a rigid motion that creates a new figure as a mirror image of the starting figure. It reflects it over some sort of what's called line or axis of reflection. So when we're talking about two dimensions, the figure and its mirror image are equidistant from that line. Equidistant meaning just an equal distance on either side. In the same way that you looking into a mirror appear to be an equal distance away on the other side of the mirror. So if we wanted to construct a reflection of this triangle ABC over the line L, how would we do it? Well, essentially what we want to do is measure the distance from the line to any given point. So we can see that A is 2 units away, B is 6 units, and C is 6 units. So now we want to take those measurements and sort of flip them over to the opposite side, like so. So A with an apostrophe, which we will call A prime, is 2 units away. B prime is 6 units away. C prime is 6 units away again, and they're all in the same sort of grid line horizontally as they were. So they're lined up, and we could see if I had placed a mirror on that line of reflection, it would make sense that it would be the exact reflected picture, right? If I fold this piece in half, if I fold this grid in half along that line, they would line up perfectly. That's the idea of the reflection. Next, we have a translation, also known as a glide, which is a rigid motion that moves a figure by sliding along some straight line segment in the plane. A translation is determined by the direction and length of that segment. So a concise way to indicate the direction and distance that a figure is moved during a translation is with a translation vector, which is basically an arrow from old point to new point. So here we have square ABCD and translation vector V. And we want to create A prime, B prime, C prime, D prime, the translation of ABCD along this vector. So to do this, the vector tells us the direction we're headed and how far in that direction. So essentially, we want to measure how far left, right, down, up this vector has taken the point, its starting point here. So how far away is its ending point? Well, we could think of it as 6 units down, 3 units to the left. That's sort of what's happening here. Even though it is going diagonally, it's going 6 units down and 3 units to the left. I should say it's 6 units down and 3 units to the right. Oops. So, 6 units down, 3 units to the right. Then we are going to apply this to every single one of the points on this square. So we're going to take A, go 6 units down, 3 units to the right. B, 6 units down, 3 units to the right. C, 6 units down, 3 units to the right. D, 6 units down, 3 units to the right. That's exactly what we'll do. That's what it's going to look like to glide this square along the translation vector. So we can see this right here. This is what would happen to B. Point B, if we were to move it 6 units down, 3 units to the right, we will get a new point B prime right here. Similarly, if we do that to all of our 4 points, we can see it's like sliding it along this, these arrows, and we can see it's the same shape is what's going to end up here. If I place all 4 of these points at the end of the arrows, 6 units down, 3 units to the right, then draw in the edges of the square, we do indeed have a square, which tells us we probably did this correctly, because that's the idea, is that it should be the same shape in the end, and it still is. It's still a square. Next, we have rotation. So a rotation is a rigid motion performed by rotating a figure in the plane about a specific point, called the rotation point or the center of rotation. The angle the object is rotated is then called the angle of rotation. So both the point and the angle need to be specified in order for us to know what type of rotation we are going to do. So here I have polygon ABCD, which is a parallelogram, and point P, and we want to construct parallelograms that result from a 90-degree rotation and a 180-degree rotation. So this can be tricky depending on the shape you're working with and everything, but essentially we want to think about taking, let's say, point B here and making 90 degrees, making a 90-degree angle. So if point B is 3 to the right and 1 up, then the right angle from point P would be 3 up, 1 over now. So this right here makes a right angle like so. That's 90 degrees. So we can place a point there. If we repeat, so here we have from P to A is 1 up, 2 to the left. So now we want to go 1 left, 2 down to get us to our next point. And so that'll be point A prime. D will be, so 3 left, 1 down. So we'll go 3 down, 1 right. And we can do the same thing with C to get our last point. So that's our 90-degree rotation. So you're essentially taking this L that I've made, which is a lot easier to think about rotating than the whole shape. I took the L and rotated it, right? I take this L and I rotate it 90 degrees. Take this L, rotate it 90 degrees, and so on. So we create this A prime, B prime, C prime, D prime that is a 90-degree rotation from around point P. Now to get the 180-degree rotation, we do the same thing. We take point, we can take, let's say, B again, but now we can go from B prime, and we can create our L. So up 3 over 1, now it's going to be like so, and that'll be our new point B, B double prime. And so on. So we keep doing that because 90 plus 90 is 180, right? We also have the option of thinking about 180 degrees just means we're taking the point B, the original point B, and flipping it to the exact opposite. So it was 3 to the right, 1 up. It'll now be 3 to the left, 1 down. Everything will be its exact opposite. 1 up, 2 to the left becomes 1 down, 2 to the right, and so on. So we end up with essentially the exact same shape So once we have this shape, we want to remember that we need to label the shape. So we label it, remember the previous one was A prime, B prime, C prime, D prime. The new one is going to be, we just put two little apostrophes to call this C double prime, A double prime, D double prime. Like, that's how you would say it. So this is just a way of marking that A has been moved, so the original A has now been moved over to this point. So it's not the exact same shape, it is a new or moved version of the shape. So we want to mark where did the point A move to, even though it looks as if the shape itself hasn't moved at all. Now, finally, our last type of transformation is a combination of transformations called a glide reflection. So a glide reflection is a rigid motion formed by a translation followed by a reflection. So in a glide reflection, the reflection line and the translation vector must be parallel to each other. So essentially, this means is we are reflecting over a line and moving it. So we're just doing two things, essentially. So in this case, we see that it is a new shape, but it has also been shifted. And that's it. So we took this, we flipped it over, let's see, where else did it go? So we have this point, and this point would be just the direct reflection, but we've now just shifted it up a little. And that together creates the glide reflection. So we reflect, then we shift, that's it. Or we can shift and then reflect, it doesn't really matter. So now that we have all of that, we can talk about symmetry. So a symmetry of a geometric figure is a reflection or rotation that moves a figure back onto itself. That is, the beginning position and ending position of the figure must be identical, just like they were with the 180-degree rotation of this parallelogram. We can see we can't see the original picture anymore because it ends up directly on top of it. So in fact, a 180-degree rotation is a symmetry of this parallelogram, while a 90-degree rotation would not have been. So reflective symmetry occurs when we use a reflection about line L and the ending position is identical in appearance to the starting position. We say that the polygon has reflective symmetry about line L, and we refer to line L as a line of reflection. So we can think of it as, if we have this star, there's multiple different reflection lines that we can use, but I've noted one possible one where we're taking G and it's reflecting over to C, and C in turn is going to G, and that's what's sort of being demonstrated here, is that we're flipping the whole thing around. H becomes B, but B becomes H. A kind of stays on itself, and E stays on itself. So we end up with the new version over here, where a lot of parts have changed position, but it's still the same. A lot of the letters have changed position, but the shape itself hasn't changed position. It appears the same. So L is, in fact, a line of reflection. But if I had drawn a line here, or over here, or somewhere else, we wouldn't have a line of reflection. But I could have a line of reflection this way. I could have one this way. I could have one this way. So in fact, this shape has 4 different lines of reflection that we could use. Now, rotational symmetry, similarly, is when we rotate about a point P and the ending position is identical to the starting position. We say that the polygon has rotational symmetry about the point P and refer to that point as a point of symmetry. And we usually also note the angle at which we get this symmetry from. So, just like with the parallelogram that had 180-degree rotational symmetry, we can have 90-degree rotational symmetry here, we can have 180-degree, 270-degree rotational symmetry. We've got options for our rotations for this shape. But it's just taking the whole shape, as we can see in this picture, and rotating it around so that it lies back on top of itself once it's over. So in this case, we can see I performed a 90-degree rotation, taking A to where G is, G to where E is, E to where C is, and C to where A is. So we can see that over here. So H ends up where F is, F to D, D to B, B to H, and that's all a 90-degree rotation. But again, if I had done 180 degree, if I do another 90 or another, and then another 90, I've got 3 different options for my rotation, but it's all around this same point P that is my center point. So the last thing we're going to talk about is a thing called tessellations. So a tessellation, or tiling, is a pattern consisting of the repeated use of the same geometric figures to entirely cover a plane, leaving no gaps. The geometric figures used are called the tessellating shapes. The simplest tessellations use one singular regular polygon. This works with equilateral triangles, squares, and regular hexagons. I say this because those are the only regular shapes that it works with. So of course we could tile with rectangles if we wanted to. If I can do it with squares, let's make these wider, right? I can do it with rectangles. Pretend that's actually a rectangle if that's a straight line. But the point is when it comes to regular shapes, remember regular means shapes, polygons that have all the same sides and all the same angles. Only squares, equilateral triangles, and regular hexagons will tile. If I picked a regular pentagon, which looks approximately like this, but again, picture that with the exact same length, sides, and same angles, this will never tile. It will end up it's hard to draw, but it will end up with this, see this wide region that I can't really fill in with the exact same shape. Again, I'm trying to draw it out, but it's hard to be precise when I'm doing it by hand. But you can see that that if you try it with other shapes, if you go into some drawing program and attempt to copy and paste a regular pentagon, for example, you're not going to be able to what's called tile the plane. They won't lie next to each other perfectly. But we can use a lot of irregular shapes to do this instead. There's plenty of interesting shapes that you can make that will tile the plane, but when it comes to the regular ones, these are the only ones that we can use, which is why we see these in a lot of situations like actual tiling on bathroom walls or kitchen floors, or if you're into board games, we tend to use square tiles, triangle tiles, or hexagonal tiles. Anything like that, those are the only options. That's why you're not really going to see a board game that uses pentagonal tiles or octagonal tiles to make a grid, because they literally cannot do that. But tessellations have been around since ancient times. Like here is an example of one from ancient Egypt. Tessellations are how we make mosaics, how we make again, the tiling on your floor. You see these in everyday life all the time. And in fact, here is one way that you could create your own tessellation by taking really any of the shapes I just talked about, but specifically the square is the easiest one to work with in this manner. We begin with the square. We can draw a line or curve from top to bottom and cut it apart. Sort of shift this cut piece right here over to make this. Then, wrong one. To make this. Then repeat by cutting down the middle again and shifting that to make this new piece. If you follow those steps, you can create this sort of odd, irregular shape that's got some sort of, it's not even a polygon, it's got rounded pieces. But we can kind of see how it would have to fit together. This and this are the same, right? Or this and this are the same, right? So they are going to fit together, and in fact, once we take this, we can then trace the shape on a blank piece of paper, move the shape, lining it up with any drawn figure and keep tracing, we'll see that it in fact does create this pattern that we can make, and that is how we form tessellation. So that's something, sort of a fun thing that you can do on your own to make some cool patterns.